All right, welcome back to another lecture. In this video, we're going to cover section 3.6. And the purpose of this lecture is really to try to tie together a little bit better some stuff that we did in Unit 1 and the stuff that we've been doing in Unit 3 with inferential statistics. So we want to tie together the descriptive statistics from Unit 1 with the inferential statistics in Unit 3. A really helpful perspective here is to, instead of thinking about the different groups that we're comparing as coming from two different data sets or two different samples, instead we can think of them as coming from the same sample which has different variables, right, in it. And so instead of thinking of comparing two different data sets, we're going to think about comparing two variables within the same data set. And I'll show you what I mean by that in a second. The reason that this is useful for us is because oftentimes the comparisons that we're making are really, if you kind of step back and consider it from a different perspective, what we're really doing is trying to determine if the variables in the data set are independent or if there's some kind of correlation or association between the variables. For example, suppose that a data set has two variables in it, gender and height. Right, gender and height. It would be natural to wonder if gender affects height. In other words, we want to know if there's some kind of association between these two variables or if they're completely independent of each other. And so we'll spend some time over the next several sections kind of revisiting many of the hypothesis tests that we've discussed and reframe them as tests for independence. And our goal is to determine when two variables are correlated or associated. And I'll use a lot of different terms more or less synonymously, but correlated or associated or dependent or contingent, right? The first step in this process, of course, is to do some good descriptive statistics. And so in this section, we're going to review a little bit about describing data sets, what we know about describing data sets from Unit 1, and we'll adapt that knowledge to studying interactions between variables. So we're not going to do we're not really going to do any hypothesis testing in this section. It's just going to be mostly kind of a review of Unit 1, but giving it a different perspective, okay? So far, we've been dealing with situations like this, where you have a small group of kids and adults were asked if they like pineapple on their pizza, and we're given the data nicely grouped by age group, okay, kids and adults. In Excel, those two data sets might look something like this, right? But raw data actually rarely begins this way. Usually the raw data looks something like this, okay, where the two variables in question here are whether they like pineapple on their pizza and what age group they belong to. And so instead of automatically splitting up the pineapple column by age group as has been done here, usually it's all just kind of jumbled together into one big data set. And so these are the kinds of things that we want to be able to handle, okay? So just talking about this data set a little bit, when you're dealing with a data set like this, each column in the data set is a variable. So whether or not they like pineapple on their pizza is a variable, and age group is a variable. In this situation over here, kids and adults are not variables. Kid and adult are just the possible responses to the age group variable in the original data set, okay? That's a little bit tricky to kind of wrap your brains around sometimes, but when we're trying to describe whether or not the variables in the data set are independent, we're not trying to describe if kids and adults are independent. What we're trying to describe is your preference for pineapple on your pizza independent of your age group, right? So it's not the kids and adults that we're trying to decide if they're independent. We're trying to decide if pineapple and age group are independent. The columns in the raw data on the right represent the two variables in question. The rows represent individuals. Okay, So this individual right here, for example, is a kid who does not like pineapple on their pizza. Okay, so each column in a data set like this one, each column represents a variable and each row represents an individual. Okay, that's not true of a data set like this one. Okay, so really the data set here on the left is an organized version of the raw data on the right. Okay, what we've done basically is we've taken the data on the right and we've split the responses in the pineapple column by the responses in the age group column. We'll learn how to do this, so let's practice doing that. It's not going to be always a super useful thing for us to do, but in some situations it is. All right, for certain types of variable comparisons, this is a very useful thing to do. It's not so useful in this particular scenario, but we can do it. And so let's learn how to do it so that we know how to do this in cases where it is useful. So to do this in Excel, well, you'll split a column by basically just by sorting the columns, and then you can manually split them. So you can go to custom sort from the sort and filter tool in Excel. You can also get there by just right-clicking and then clicking on sort. So let me give you an example. We'll use this exact example. A small group of kids and adults were asked if they like pineapple on their pizza, and then we're asked to use Excel to split the pineapple column by the age group column. And then we're asked to do it the other way around, split the age group column by pineapple preference. So let's head over to Excel and do this. Let me zoom in a little bit. Okay, so we've got our two columns, our two variables here. Do you like pineapple on your pizza? And what's your age group? Are you a kid or an adult? And we're asked in part A to split this column by age group. So what we'll do is we'll select our data set. You can either select just one column or you could select the whole thing, but then you're going to go to sort and filter and custom sort. Let me just show you what happens if you only select one column. If you go to sort and filter and then custom sort, you'll get this little window that asks you, do you want to expand the selection or just continue with only the column that you've selected? If you continue with only the column you selected, then it will sort this column and leave this column fixed, which is not what you want, because you want the individuals, each row, to remain connected. Okay, so you should say, yes, expand the solution, right? And then it selects the whole thing for you. We want to sort by age group. And so now it puts all the adults at the top and all the kids at the bottom. We could now manually create an age column not an age. We can create an adults column and a kids column, and then we can just copy and paste the pineapple responses for all of the adults into the adults column, and for the kids into the kids column. And that's how we would split the pineapple column by age group. If we wanted to split age group by pineapple preference, well, we would do the same thing, right? We would select the data, go to sort and filter, custom sort, and this time we want to split by pineapple preference. So we say okay. It puts all the no's, okay, together and all of the yeses together. And so then we can say we can create a column for yes and a column for no, and say, well, all of the no's, these were all of the no's, so I can put them there, and these were all of the yeses, so I can put them there. Anyway, doing this now, you could look at the proportion of adults who like pineapple on their pizza and compare that to the proportion of kids who like pineapple on their pizza. You could then, run a hypothesis test with that. You could also, using the Art of Stat web apps, you can just put the raw data in and it'll know how to handle that situation. We'll practice that later. But if you wanted to separate it, you could also do it this way. And then the same thing here. You could say, well, what proportion of people who said yes were adults, and what proportion of people who said no were adults, right? And then you could compare those two groups a little bit more easily. So that's the idea with number one. You might hear my dog snoring in the background. Okay, number two here asks us to do a similar thing. It says a group of children were asked questions about their favorite Pokemon, their age, their height, and whether they prefer grapes or raisins. And then part A asks us to use Excel to split the favorite Pokemon column by grapes or raisins preference. And then part B asks us to split the age column by grapes or raisins. Let's head back over to Excel and do that. So moving over to example 2. Okay, so if we want to split the favorite Pokemon column by grapes or raisins, I'm just going to select the whole data set and I'm going to sort, custom sort, and I'm going to sort by grapes or raisins. Okay, so everything gets rearranged and you'll see that grapes and raisins are now split into their groups, okay? So if I want to split up the favorite Pokemon column, this column, by grape or raisin preference, then I can create my labels, grapes and raisins. Whoops. And I can say, well, these were all the favorite Pokemon characters for kids who liked grapes. And these were all the favorite Pokemon characters for kids who liked raisins. Okay, and now I have like two different columns, the way that we are used to seeing them. Okay, this is not a super helpful thing to do in this particular case because, well, the sample sizes are so small, right? And there's so many unique observations. Like, I don't think we're going to get really a ton of useful information here. But part B asks us to use Excel to split the age column by grapes or raisins, and this I think is maybe a little bit more useful. It's already organized by grape raisin preference, so I'm just going to make my two columns for the ages, right? Grapes, raisins, and I can put the ages in there. So these are the ages of people who liked grapes, and these are the ages of people who preferred raisins. And we could now, the reason I think this is more useful is because now we could compute the average age, for example, of people who like grapes, and we could compute the average age of kids who like raisins, and we could see if there's, a discernible, difference between those two groups, right? See if maybe kids who like raisins are a little bit older on average or something like that. I don't have any reason to suspect they are. I think that these are pretty similar data sets, but you could do that, right? You could compute standard deviations and so forth. Okay. So when you are comparing something like a numerical variable like age by a categorical variable like grapes or raisins, splitting the data like we just did can be a useful thing, right? Because with the data separated into columns, we can compute means or medians or standard deviations or anything else that we want. And that way we can see the effect that age has on a child's grape or raisin preference. Again, note that the variable comparison we're making is not grapes versus raisins, right? We're not comparing grapes versus raisins. What we're comparing is age versus grape or raisin preference, okay? Anyway, so splitting a numerical variable by a categorical variable can be very useful. Splitting a categorical variable by another categorical variable is not quite as helpful. What's more helpful in that case is to create a contingency table. As we've done in the past. So let's review a little bit about contingency tables and review how to make them in Excel. So a contingency table, as we know, shows the frequencies of two variables by arranging the possible responses of one variable in rows and the possible responses of the other variable in columns. So that much we know already, okay? This would be an example of a contingency table. So we have favorite Pokemon character broken down by grape and raisin preference, okay? Something that's maybe a little bit new is the idea of a conditional distribution. So to construct a conditional distribution of variable A by variable B means to compute the proportion of observations in each cell of the contingency table relative to variable B. Here would be an example of a conditional distribution. This is a conditional distribution of Pokemon by preference, by grape or raisin preference, okay? In order to get these proportions in here, what we do is we divide each cell by the column total because preference was the column variable, okay? What I mean by that is the column variable is this variable right here. It's how you split up your columns, right? This is your column variable. And in this case, it's preference, right? This is your row variable, right? The row variable is your favorite Pokemon, right? So in order to get these, what we've done is we took the column total in our original contingency table, and we found the total, right? We got the column 1 total and the column 2 total, and we divided 1 divided by whatever this column total was to get this percentage, okay? So this is what it means to build a conditional distribution of a row variable by a column variable. We could do this the other way around. We could create a conditional distribution of a column variable by a row variable. And in that case, what you would do is you would divide these numbers by the row totals, right? In this case, this is a little easier because we know that the row total for this top row is 2. And sure enough, 1 divided by 2 is 0.5, right? And 1 divided by 2 is 0.5. And 2 divided by, well, the row total here would also be 2, is 1. 0 divided by 2 is 0, right? And so this is how they're getting these numbers. So again, if you want to create a conditional distribution of a row variable by a column variable, then you divide by the column total, okay? If you want a conditional distribution of a of a column variable by a row variable, then you divide by the row totals in the contingency table. Anyway, making a contingency table to compare a categorical variable to another categorical variable is useful. It helps us to see certain trends, right? For example, we could say kids who like Bulbasaur are equally likely to prefer grapes or raisins, right? We get that from this row right here. We can see, oh yeah, kids who like Bulbasaur equally likely to prefer grapes or raisins. And by the way, this is a very small sample size, so we wouldn't have much confidence in our observations, but I'm just trying to give you an example, and we'll look at some better examples later. Another observation from this is that kids who like Eevee prefer grapes over raisins, okay? 100% of kids who liked Eevee preferred grapes. We can make observations from the other conditional distribution as well. Among kids who prefer grapes, 33% are EV fans. In other words, if you just restrict your attention to kids who like grapes, right, 33% of them are EV fans. And if you just restrict your attention to kids who like raisins, 60% of them are Pikachu fans, and so forth. Again, overall, it's hard to make a lot of comparisons here. It's difficult to say if there's much of an association between favorite Pokemon and grape raisin preference because the sample size was just too small here. But let's practice making these conditional distributions in Excel, right? We can use pivot tables to make contingency tables and to make conditional distributions. So number 3 here says to use Excel pivot tables to practice making the conditional distributions above for the data from example 2. And then, does there seem to be any association between favorite Pokemon and grape raisin preference? Well, we've already talked about that, right? There's not. It's hard to say, but we can practice making the conditional distributions. So let's do that. Okay, so this is from example 2. I'm going to delete the work that we did for the previous example. And let's zoom in a little. Okay, and let's use pivot tables to do this. So I'm just going to select all of the entire data set, and I'm going to go to Insert, Pivot Table. We've done this many times. I'm going to go ahead and put mine in the existing worksheet. I'll put it right there. Say OK. So now I can build my pivot table. If I want to build a contingency table of favorite Pokemon by grape or raisin preference, then I can start off by dragging favorite Pokemon to rows, okay, and then dragging favorite Pokemon over to values, okay, and this is the same kind of pivot table that we've made in the past. Okay, this is a frequency distribution now that counts up the number of people who, or the number of kids who said Bulbasaur, Charmander, etc. But now if I want to split that, up by grape or raisin preference, then I can take the grape or raisin variable and drag that to columns. Okay, and now it gives me, now it breaks this down in terms of grapes or raisins. This is my contingency table. I might want to have zeros here instead of blanks. So in order to get Excel to do that, I just select a row and then right click it and go to Pivot Table Options. And then under Display, or actually no, here under Layout and Format, where it says for empty cells, show 0. And say OK. And now those zeros will show up in those blank places. Okay. Now, if I want to make this into a conditional distribution, okay, of Pokemon by preference, right, by grape raisin preference, then what I can do is here under Count to Favorite Pokemon, I can go to Value Field Settings, and I can show values as, and if I want to give a conditional distribution by grape or raisin preference, well, grape raisin preference is my column variable, and so I want to do % of column total, and now it does those calculations for us, okay? If, on the other hand, I wanted a conditional distribution of preference, grape raisin preference, by favorite Pokemon, well, then I would want to if I want to break it down by favorite Pokemon, that's my row variable. So what I will want there are row percentages. So I can go to Value Field Settings, show values as % of row total. Okay. So either of those conditional distributions I think should match pretty well with what we had above in the notes. Number 4 here says use Excel pivot tables to create a conditional distribution of the proportion of people who like pineapple on their pizza by age group for the data from example 1. Does there seem to be any association between age group and whether a person likes pineapple on their pizza? Well, let's head back over to Excel and do this for example 1. Okay, so coming back to example 1, I'm going to erase all of our work from before. And let's insert a pivot table. So I'll select the columns, go to Insert Pivot Table. I'm going to put it in the existing worksheet right there and say OK. And we want a conditional distribution for the proportion of people who like pineapple on their pizza by age group. So I'm going to drag pineapple to rows and pineapple to columns. So this is just a small little frequency distribution, okay? But if I want to split this up by age group, then I can drag age group over to columns, okay? And so now I have things broken up by kids and adults. It says that we want to give a conditional distribution for the proportion of people who like pineapple on their pizza by age group. So we want to do this by age group. Well, age group is our column variable, right? Age group is our column variable. So I will display the count of pineapple as a percent of column total because I want to split by my column variable. Okay. So let's interpret this a little bit. What we're saying is that if you're an adult, then you're equally likely to say that you like pineapple on your pizza or that you don't like pineapple on your pizza. If you're a kid, on the other hand, then you're far more likely to say that you do not like pineapple on your pizza than you are to say that you do like pineapple on your pizza. So to answer the question, does there seem to be any association between age group and whether a person likes pineapple on their pizza? I would say yes. Kids are far less likely to enjoy pineapple on their pizza than adults are. Okay? So let's write that down. So I would say yes. Kids are far... Whoops. I put the E in the wrong place. Sometimes I feel a little dyslexic, you know. Kids are far less likely, only 16.7% of them, right, to like pineapple on their pizza than adults. For adults, 50% said that they liked pineapple on their pizza. Okay. So that's how conditional distributions work. Again, they're very useful for comparing two categorical variables. I want to introduce a new kind of graph to you called the scatter plot. I think scatter plots are more or less fairly self-explanatory, and you've probably seen them before, but we haven't talked about them in this class, and so let's talk about them here. Scatter plots are really useful for comparing two numerical variables, okay? In fact, if you have two numerical variables, it's really not going to do you much good to create a contingency table or to try to split one column by the other, because if both of the variables are numerical, the chances are there's going to be a very wide variety of possible responses. And so you're just not going to be able to make much sense of it if you make a contingency table or something like that. So a much better thing to do is to create a scatter plot. A scatter plot is a graph that allows us to analyze the association between two numerical variables by treating each individual as an ordered pair xy, where x and y are the individual's responses, and plotting those ordered pairs in the Cartesian plane. That sounds really fancy, but it's straightforward, and you've done this before for sure in your algebra days. I'm sure that you plotted some points once upon a time. So just to give you an example of this, the number of absences and the final grade of 7 randomly selected students from a statistics course are given below. So we have this is one individual. This individual missed class 6 times, and their final grade in the course was an 82%. That corresponds to this point right here. Okay, they missed class 6 times and ended up with an 82% in the class. Okay, and if you do this for all of the remaining points, right, like this student missed class 12 times and ended up with a 58% in the class. That's this individual right there. Okay, so if you plot all of these ordered pairs, then you can get a visual sense for whether or not there's a correlation between absences and your final grade in the course. In this case, I think there is a fairly clear trend, right? It looks like as the number of absences increases, the final grade decreases. Okay, we would say that there's a negative correlation between these variables because the slope of this line is negative. In general, scatter plots are really useful. They tell us information about how strong a correlation is, right? This would represent a very strong correlation. This would be a kind of a weaker correlation, but there's still somewhat of a trend. And this one would represent no correlation whatsoever. Scatter plots also tell us about the direction of a correlation, right? A positive correlation, negative correlation, no correlation. Okay. They also tell us about the shape of the correlation. You could have a linear correlation where the points fall more or less on a straight line. You could have an exponential correlation where the points fall on an exponential curve. You could have like a parabolic correlation, a U-shaped thing, all kinds of stuff. These types of correlations are beyond the scope of our course, so we're going to focus mainly on linear correlations. But scatter plots are useful for helping us determine these things. What type of correlation, if any, do you think exists between absences and final grade? Well, I've kind of given that away, right? I think there's a negative linear correlation between absences and final grade. A negative linear correlation. The more you miss, the lower your grade. Making scatter plots is really easy in Excel. We just highlight the variables and then insert a scatter plot. We don't even have to do a pivot table or anything. So number 5 here says make a scatter plot for the age and height columns in example 2, and then what type of correlation, if any, exists between age and height. So let's head over to Excel and do that. So going back to example 2, we want to make a scatter plot for the age and height columns. I would guess that these things are positive, that there's a positive correlation between those variables, because it seems like, if you're a kid, the older you are, the taller you're going to be. But there's only one way to really know that. We'll select the columns and then go to Insert. And the scatter plot is this one right here. So we'll insert a scatter plot. And that's that. You can kind of adjust the X and Y variables like we have before to get a better picture. So I can go to Format Axis and just say, I could probably start at 40 instead of starting at 0. Okay, and then I can do the same thing for the X-axis. I can select this axis, right-click it. I didn't quite get it. Right-click the axis, Format Axis, and then maybe I can put the minimum at, well, the minimum is 6, but if I put it right at 6, it's going to be weird. Maybe I'll put the minimum at 5. Anyway, now you get a better picture. And you can see that, okay, yeah, there seems to be a positive linear correlation. You can add a trend line and kind of see, oh yeah, there's a positive linear correlation there for sure. Okay, let's write that down. So there is a positive linear correlation between age and height. In other words, the older a child is, the taller they are. Okay, that's not surprising to anyone, but that's what the data there seem to suggest. Okay, so at this point, I think that we have kind of talked about some of the key tools that we would need to perform some kind of descriptive analysis when we're trying to compare variables within a data set. And I just want to take a brief moment and kind of summarize those things, okay? So you may recall, often the objective of research is to determine how changing the value of an explanatory variable, the cause, affects the value of a response variable, the effect. We saw this in various questions that we've asked so far. Does age group affect whether someone likes pineapple on their pizza? If it does, we would say age group is an explanatory variable and their preference is response. Does gender affect height? Okay. Does number of absences affect final grade? And so forth. So the way we answer these kinds of questions is by exploring the interactions between the variables in question, and we can broadly group the possible kinds of interactions into three groups. We might have a case where we are comparing two numerical variables, right? Does the number of absences affect your final grade? And a scatter plot is a really great visual for that comparison. We would also want to look at something called the correlation coefficient, and this is going to be the topic of discussion in 3.7. We'll look at the correlation coefficient, and we'll introduce a hypothesis test that I'm just going to call the linear correlation test to explore that relationship of a numerical variable versus a numerical variable. Looking at the slope of the best fit line would also be an important thing to do. So we'll talk about the linear correlation test and the correlation coefficient and all of that in 3.7 for comparing two numerical variables. If you want to compare two categorical variables, like does age group, kid, adult, affect liking pineapple on their pizza, yes or no, right? Those are both categorical variables because the answers are not numerical, right? They're words. Here, what we would want to do is compare the proportion of people in each age group who like pineapple on their pizza, which is something that we actually did in one of the previous examples in this lecture. Comparing modes and IQVs, right? Index of qualitative variation, those might also be useful things to do. In which case, it might be helpful to split the columns, okay, by pineapple preference or whatever. But for sure, contingency tables are going to be useful whenever you're comparing a categorical versus a categorical variable. And a good graph is a side-by-side bar chart, okay? That would be a great visual for this kind of comparison. Because we're comparing proportions, the hypothesis test to run would be a two-sample proportion test or a homogeneity of proportions test, depending on how many categories you have for each of your variables, okay? So that will be the topic in section 3.8, okay? But we'll practice doing sort of the descriptive part of it in this section. And then finally, okay, if you have a categorical versus a numerical variable, like does gender affect height, right? Male, female versus how tall you are, right? So we have a categorical variable, gender, and then a numerical variable, height. How do we make that comparison? Well, what we would want to do is compare the average, right? Either the mean or the median height for each gender. So here it would be really helpful to split the raw data by the responses to the categorical variable. So we want to split the raw data from the numerical variable by the categorical variable. And we can draw some histograms to determine the shape of each distribution, right? If they're symmetric, then we'll compute and compare the means and the CVs. If at least one of them is skewed, we'll compute and compare medians and QCVs. A side-by-side box plot would be a really good visual for this comparison. And then since we're comparing the means of the groups, we would either run a two-sample t-test, okay? If our categorical variable only has two categories, then we'd run a two-sample t-test. If our categorical variable has more than two categories, then we'd run an ANOVA. That'll be the topic in 3.9. But again, we'll practice a little bit in this section, just doing kind of the descriptive statistics here. Whether you're doing a numerical versus numerical, or a categorical versus categorical, or a categorical versus numerical, all of the tests could be described as tests for independence. And we'll spend, again, 3.7, 3.8, 3.9 kind of introducing a new test in the case of 3.7, but in the case of 3.8 and 3.9, sort of reintroducing the two-sample proportion test, or the ANOVA test, right, as tests for independence. So that's kind of an overview of what we have to look forward to. Here's a table, right, that might be useful. That kind of summarizes the things that we've talked about in this lecture. Okay, if you want to compare two categorical variables, making a side-by-side bar graph is very useful. In order to do that, you first have to get a good contingency table and get a good conditional distribution for whatever comparison you're trying to make, right? The statistics to compare would be proportions, and a hypothesis test to run would be homogeneity of proportions or two-sample proportion, depending on how many categories you have. For a categorical versus numerical comparison, we would make a side-by-side box plot. It would be very helpful to split the data, okay? Split the numerical variable by the categorical variable, and then we can compute the means and the medians of each category, okay? And then run an ANOVA or a two-sample t-test. And then finally, if you're going to compare two numerical variables, best thing to do is to make a scatter plot. You might want to look at the slope of the best fit line. You'd also probably want to look at the correlation coefficient, which are things that we'll talk about in the next section. And then the test you would want to run is the linear correlation test. So what I want to do in example 6 is I'm not going to write anything down, I think, for any of these problems, but I do want to just kind of talk briefly, just make these comparisons. We'll go over to Excel and we'll make each one of those comparisons and kind of talk about what we observe in the data. So let's head over to Excel. And you of course can write some things down as we go through these examples. But in example 6 here, we've got a whole bunch of variables. Remember that in a data set like this, each column represents a variable. So we've got shoe size is a variable, homework score is a variable, test score is a variable, whether or not the individual took a practice test, right, is a variable. Their handedness, right, left-handed or right-handed, is a variable. Seat position in the class, whether they're sitting in the back or the front, that's a variable. And each row represents an individual. So this individual right here wears a size 12 shoe. They got a 28.2% on their homework scores and 30% on their test. They didn't take a practice test. They're left-handed and they sit in the back of the class. Okay, so that's how we would interpret this data set. In part A, we are asked to compare shoe size versus test score. And I think what I'm going to do is I'm just going to copy and I'm going to open up a new sheet down here. I'm going to click on this plus sign to open a new sheet. And then I can paste test score. And I want to compare test score versus shoe size. So I'm going to take shoe size, copy it, and paste it. You don't have to do this. You could do this right there in that very same spreadsheet. But I'm going to do this in a new sheet so that I don't get confused. So, okay, to select my data, I can do Control Shift down and then right, and that'll get all of it. Or you could do Control A, and that would also get all of it. These variables are both numerical variables. So the best thing to do here would be to make a scatter plot. So I'm going to insert scatter plot. And I can even add a little trend line. And I don't know about you, but to me, it's very apparent looking at this that there is no association whatsoever between test scores and shoe size. We've got our test scores down here on the x-axis and our shoe size up here. It doesn't seem like your test score has any bearing whatsoever on your shoe size, or vice versa. It doesn't seem like your shoe size tells you anything about what your test score is going to be. And that's not a huge surprise, right? There's nothing there. Because these variables are both numerical, sometimes students have a tendency to want to compare the means of these two groups. But let me just point out that that would be wildly inappropriate here. Of course, the average shoe size is going to be something like, maybe 8 or 9, whereas the average test score is maybe going to be somewhere around 70. So of course the average test score is bigger than the average shoe size. What useful information does that give you? It doesn't give you any useful information, right? We don't want to compare means in this case, even though we have two numerical variables. What we want to compare are just, is there some kind of trend where as your shoe size increases, your test score increases or something like that? And here we can see clearly that that's just not the case at all. Okay. In part B, we're asked to compare homework score versus test score. So I'm going to do the same thing. I'm going to take homework score, copy it. I'm going to make a new sheet, paste it, and test score, copy, and paste. Here, I think I do expect to see more of a correlation. I'm just going to say Control A to grab all of my data, and I'm going to insert a scatter plot. Look at that. Okay, look at that correlation. We can add a little trend line. These are real values, by the way, from past classes and stuff. Actually, that's not true. I think I did make this up. Look at that trend line, though. So clearly there's a trend. Here we have, let's see, which one did I select first? It was homework scores first. Maybe I'll pull this up to the top. Okay, so we have homework scores along the x-axis and test scores along the y-axis. And what we see here is there's clearly a positive linear correlation. As your homework scores improve, your test scores also improve. That's just not a huge surprise to anyone. There are, of course, some people who do as much homework as possible and still end up with like a 60%, right? This individual is somebody who got a 96% on the homework but only scored a 62 on the test. So that's sad, but it happens, right? On the other hand, there are individuals who don't do very much homework and do relatively well on tests, right? So that also happens. But in general, the trend is that the more homework you do, the better you perform on tests. So that's that comparison. Let me put these in order. Okay, so that's part B. Let's look at part C. For part C, we want to compare practice test versus test score. So practice test is whether they took the practice test. I'm going to copy that column. And let me move this over. Paste it into this new sheet. Uh-oh. We copy, paste. Okay. And then I want to compare that to the actual test score itself. Copy. And paste. Okay, notice that this time I do not have two numerical variables. Practice test is a categorical variable and test score is a numerical variable. So I'm not going to make a scatter plot. In fact, if you try to make a scatter plot, I don't think Excel will handle that very well. Like, it's not going to do anything useful for you. I think what we want to do here is, since we're comparing a numerical variable to a categorical variable, what we want to do is split our numerical variable by our categorical variable. So I'm going to select the data, okay, and then I'm going to go to sort and filter and do a custom sort. And I want to sort by whether or not they took the practice test. Okay, and I'll hit OK. And now you can see it puts all the no's together and then all of the yeses together. And I can create two columns now where I have, I can create two columns where I have no and yes. And then I can put the test scores for all of the no's together into one column. Okay, copy and paste. And then I can put all of the test scores for the yes column together. Copy and paste. What I could do now is make a box plot, right? So I can grab this data and create a side-by-side box plot. Let's add a legend so I know which group is which. Oh. Okay, so you can see in the box plot that the people who took the practice test did better on average than the people who did not. In fact, you can see the mean and the median are both larger for people who took the practice test than they were for people who did not take the practice test. Okay, so that's interesting. If I wanted to, I could also compute the means, right? Or the medians. So I could say yes and no. Let me move those down, actually. Yes and no. And then I can put the mean, the median. If you want, you could do the standard deviation. I'm not going to do all of this stuff. But anyway, you could do a whole bunch of stuff here. So for the yeses, I would say equals average. Okay, we remember doing this. And then I'm going to select the yes column, right? Control-Shift down to get all that and say enter. So there's the average test score for people who took the test. For people who didn't, same thing, equals average. Okay, and I'm going to select the data, Control-Shift down, enter. And okay, yeah, you can see a huge difference, right? Anyway, you could do the same thing with medians and standard deviations. So that's the idea there. Whether you should be comparing means or medians depends on the shape of the distribution. So one thing that would be useful for us for sure would be to get a histogram. And that would require us to make a pivot table of each of these. So we could take the no's, Control-Shift down, and insert a pivot table. And let me just put my pivot table in the existing worksheet right there. And I'm going to drag the no's to rows. I'm going to drag them to values. Remember, I don't want to sum up the values. I want to count the values. And I probably want to group into classes, right? So I'll select one of these rows and say group. And maybe I'll just use the default settings that Excel wants to do. And then I can select that and insert a bar chart. And there's a histogram for us, right? So it's been a while since we've done these things. We should make the gap width. Let's format data series so we can make the gap width like 2%. Hopefully you remember doing all of this stuff before. Anyway, but we can look at the shape of the distribution for no's. We could look at the shape of the distribution for yeses. And if at least one of them is skewed, then we should probably use medians and QCVs to make the appropriate comparisons. I would say that this one is slightly skewed left. And looking at the box plot also looks kind of skewed left, right? A little bit, like this left whisker is a little bit longer than the right whisker. So I would probably want to compare medians here. But anyway, that's the idea. The hypothesis test we would run would be a test on the means, because even though the data are skewed, we have more than 30 observations for each data set. So our conditions for running a test on the mean are met. Okay, so that's part C. Here I would definitely say yes, there's a correlation between test score and whether or not you took the practice test. There's a pretty clear correlation to me, right? Look at the means, look at the box plots. Pretty clear correlation between those variables. Okay, let's look at part D. So part D asks us to compare seat position in class versus test score. So I'm going to take seat position in class, copy that, and paste it. Let me move this over. Okay, and I want to compare that to test scores. So copy and paste. And it looks like the same thing now. I'm comparing a categorical variable to a numerical variable. So I'm going to want to split. Let me do Control A to grab all the data. And then I'm going to sort, do a custom sort. And I want to split the columns by position in class. So I'm going to sort by seat position in class. And it looks like maybe those were already sorted for us. What are our options? We have people in the back, people in the front, people in the middle. So it looks like we have 3 categories this time. Okay, so I'm going to make 3 columns: front, back, and middle. And I can take the test scores of all of the students in the back of the class, put them in the back column. I can take the scores of people who sat in the front of the class. That's all of these guys. Copy and paste. And I can take all the people who sat in the middle of the class, these ones. Copy and paste. Okay, and now I can do a side-by-side box plot to get some sense for what's going on here. So I'll highlight those, go to Insert, and let's do a box plot. So this is kind of a surprising result to me. Let's add a legend. So, okay, so there does seem to be a difference in test scores between people who sat in the front versus people who sat in the back. People who sat in the back did much worse on average, right? Their median and their average scores are both lower. People who sat in the middle, they seem to be more or less on the same line as people who sat in the front, okay? So would we say there's a correlation? Yeah, I would say so. I think that there's a correlation here. I think that you're less likely to do well on the test if you sit in the back of the class, right? That's what this seems to indicate. And again, we might want to look at means, right? You could calculate the mean for each of these groups. I'm not going to review how to do that here because you should know how to do that, right? You just say equals average to get the mean. You could compare the medians, right? You say equals median to get the median. You could compare standard deviations or IQRs and so forth. Let's see. We would also maybe want to look at the histograms though, right? To get some sense for what the shapes of each of these distributions are. We could actually see that in the box plots themselves. So I'm going to do this in the existing worksheet, maybe right about there. Okay, I don't want it to sum up. I want it to count. And let's group into classes. We'll just use the default setting that Excel gives us, and we can make a histogram. So insert little bar chart. We can make the bars a little wider, get rid of that total thing. Format data series to make the gap width smaller. Okay, and there you get a picture of that distribution. You could do the same thing for the other two. And again, if at least one of these distributions is skewed, then you should probably be comparing means just for a descriptive statistic. You should compare means. You should maybe compare QCVs. But as far as the hypothesis test that we would run, we're not going to run a two-sample t-test. We're going to run an ANOVA test, because this time we have 3 categories, right? So here we only have 2 categories. So we would compare, and we'd be comparing the means of these 2 columns. So we'd run a two-sample t. Here we have 3 categories. So we would run an ANOVA, right? So 3 categories. We still compare the means. We have fairly large sample sizes for each of these groups, so the conditions are going to be met for sure. Okay, let me give you 2 more. I know that this is another kind of long lecture, but just for the sake of completeness, let's see what happens when we are comparing something like seat position in class to handedness, right? Is where you sit in class somehow associated to whether or not you're left-handed or right-handed? Again, I'm going to drag this over. Well, this time we don't have any numerical variables, okay? We have 2 categorical variables. And I think the most useful thing to do when you have 2 categorical variables is to, first of all, make a contingency table. So I'm going to say Control A to grab all of my data, and I'm going to insert a pivot table. I want to do this right here in this spreadsheet, and I'll just put it maybe right there. Okay, if we want to see whether, well, what do we want to discuss here? Maybe our hypothesis is that if you're left-handed, you're more likely to sit in the back of the class or something. I mean, I don't know. I have nothing against people who sit in the back or people who are left-handed. I have no reason to suspect this might be the case, but let's just say that that's our hypothesis, right? That left-handed people are more likely to sit in the back of the class. What we would want to do maybe is drag handedness over to rows and to values, okay? So that we get the number of left-handed people in the class and the number of right-handed people in the class. And then we can take seat position in class and drag that over to columns. And now we get a sense for where these people are sitting, right? If you're left-handed, 7 of the left-handed people sat in the back and 2 of them sat in the front. Whereas for right-handed people, 28% of them sat, or not percent, 28 of them sat in the back and 31 of them sat in the front. So if you're right-handed, it looks like you're slightly more likely to sit in the front than you are to sit in the back. Whereas if you're left-handed, then you're slightly more likely to sit in the back than you are to sit in the front. So it looks like that wild guess that I took turns out to be maybe somewhat true, right? It seems like left-handed people are maybe more likely to sit in the back of the class. It might be good for us to get a conditional distribution so that we have some understanding of what proportions there are here. So to kind of test my hypothesis that left-handed people are more likely to sit in the back, what I would want to do is get a breakdown in the percentages of left-handed people in the back versus the front versus the middle. And so I think what I want to do is get row percentages, okay? So under values, I'm going to go to value field settings and show values as % of row total. And now I can see that, 58% of left-handed people sat in the back and only 16% of them sat in the front. Whereas only 30% of right-handed people sat in the back and 34% of them sat in the front. So right-handed people are twice as likely to sit in the front as left-handed people, right? So hopefully you can see how creating a conditional distribution like this can be very useful when you're trying to compare two categorical variables like this. Is there an association between handedness and seat position in class? Yeah, I would say so. What hypothesis test would we run? Well, we would run a homogeneity of proportions test. We would want to know if left-handed people who sit in the back, if the proportion of left-handed people in the back is equal to the proportion of left-handed people in the front is equal to the proportion of people left-handed people who sit in the middle, right? We want to know if P1 equals P2 equals P3. And it almost certainly does not. But that'll be something that we talk about in a future section in a little bit more detail. For now, I did mention that as far as a visual summary is concerned, you'd probably want to look at a side-by-side bar chart. So we can select this data set and we can go to Insert and insert a little bar chart. And then you can get a visual for like left-handed people versus right-handed people. These are obviously very different. These are very different distributions. They seem very different to me. Okay. And so I would say, yes, where you sit in class depends on whether you're left-handed or right-handed. Maybe left-handed people flock to the back because that's where they have left-handed desks or something, right? So it could be the case. And maybe that's a reason for the trend that we seem to be seeing. But here I would say, yes, there seems to be a correlation between where you sit in class and your handedness. Okay. One more of these, okay? So for part F, we want to compare whether or not you took a practice test to your handedness. Okay, so I'm going to compare practice test, copy, and paste, to handedness, copy, and paste. And again, I'll want to start off by creating a contingency table. So I'm going to select all my data and then say Insert Pivot Table. Let's do it in the existing worksheet right about there. Write two categorical variables. So this is the way that we'd want to do it. Let's see if whether or not they took a practice test depends on whether they're left-handed or right-handed. So here we have so far just the breakdown of people who took the practice test, people who didn't take the practice test. It's about an even split, right? Let's break that down by handedness. So I'm going to drag the handedness variable to columns, right? Okay. So if you're left-handed, then it looks like you are exactly equally likely to have taken the practice test or to have not taken the practice test. If you're right-handed, then well, it seems like a pretty equal split. Maybe you're a little bit more likely to have taken the practice test, but probably that's not a statistically significant difference. Again, if I would want to, what I would really like to have are the proportions here, right? So let's see. I asked if whether or not you took a practice test was dependent on your handedness. So I want to create a conditional distribution by handedness. Handedness is our column variable here. So I probably want to get column percentages in this case, whereas I did row percentages before. So I do percent of column total, say OK. And there you can see the breakdown, right? Left-handed people equally likely to have taken the practice test or not. Right-handed people, also more or less equally likely to have taken the practice test or not. We can get a graph of this by inserting a bar chart. Okay. This seems more dramatic than it actually is because notice the scale of our axes, right? The scale only goes from 46% to 52%. Maybe I want to format that and make the minimum a little lower so I have like a better perspective of what's actually happening here. So maybe something like that. And yeah, so you can see that there's just really not much of a difference between the left-handed people and the right-handed people, between the yeses and the nos. It seems to be a pretty equal split. So yeah, here I would say there's really not much of a correlation at all. As far as hypothesis tests are concerned, in this case, we would run a two-sample proportion test, not a homogeneity of proportions test, because we'd only have two proportions that we would be comparing, okay? P1 equals P2. So we would run a two-sample proportion test on this one, and we'll talk about that more in a future section. I think that's all I have to say. There is a little link here at the bottom of the notes that I think is kind of funny. One thing that I have to always warn you about is that correlation does not imply causation, does not necessarily imply causation. And you could follow this link and look at some funny correlations that really kind of make this very apparent, right? That there's just not really, just because two things are correlated doesn't mean that one thing causes the other thing to happen. So you could click on that and take a look through it. We're going to talk about that in more detail in the next section. And this has already been a long lecture, so I'm going to go ahead and just end it there. Thank you for hanging in until the end, and I will check in with you in the next lecture.